So it's a pleasure to introduce the last speaker of the conference to you, Joachim Hilgert. As you can see from the transparencies, Joachim Hilgert is from the University of Paderborn, and you may also guess from the title that his research field is Lie theory and applications. Let me say a few words about his vita. Joachim Hilgert had his studies in Munich. He graduated with a PhD from the Tulane University in the United States. After that, he had various postdoc appointments in Europe and the United States, and also held a Heisenberg fellowship, and then finally became a professor in 1993 in Clausthal University, where he was for some 11 years or so. And since 2004, he is professor at the University of Paderborn. And now I hand over the word to you, Joachim.
Thank you very much. And well, thanks to the organizing committee for giving me a chance to give this talk. I really appreciate that. And I'm aware of the responsibility to give this last talk. Everybody is a little tired, I suppose. People spent a long evening yesterday in town. At least some did, I know. So I try to be not too technical, even though the title may suggest otherwise. Okay, so let me tell you what I'm planning to do. First of all, I want to say a few words about the objects on which I want to do analysis, and then I will talk about my motivation for doing this. And then there will be a little material on methods. Somebody this week said methods and ideas are more important than theorems, so I want to concentrate on the methods. And so non-commutative harmonic analysis and microlocal analysis will be methods. I'll try to transport some feeling, say, for these methods. And then I will talk about a concept, these resonances, and then there will be a conclusion. Okay, so let me start with the objects I want to deal with. And as my abstract said, I want to start in a very elementary way. I want to start with classical geometries. If I talk about classical geometries, what I mean is Euclidean type geometry, points and lines. So let's be a little more sophisticated when talking about lines. So what is a line? It's the shortest connection between 2 points. Or that's a line segment, but basically locally that's what a line is. And so Euclidean geometry is R2, and these lines are actually lines as we know them. That's a classical geometry. We all know that. Then another classical geometry is spherical geometry. Then we have, well, the sphere, surface of the Earth. That's why it's classical, because seafarers used it. And the shortest connection are great circles, or pieces of great circles. We also all know that. And so this is why, for these shortest connections, if we have a set with a metric where we can measure distances, we talk about these shortest connections as geodesics. And that's where the name comes from. And then there is the third classical geometry, which is a lot younger than the other classical geometries. That's non-commutative geometry or hyperbolic geometry. And that will be more or less the object I want to take as a starting point for what I want to talk about. Here on the picture, you see the Poincaré model. That's just a unit disk bounded by a unit circle, and the shortest connections are pieces of circles that intersect the boundary at right angles. So that's what it is. That's well known too. But mind you, well, I guess everybody knows that I will switch between different models, because in some cases it's nicer to use this model. In some other cases it's nicer to use the upper half plane model. Right? So we learned this in one variable complex analysis, that you can conformally map this one to the upper half plane. So that's something I want to use too. And there again, the shortest connections are pieces of circles that intersect perpendicular to the boundary, which in that case is just the real line. Special case, I mean, when I say circle, you say, how about the diameter? Of course, the diameter is a circle of infinite radius. Okay, so these are the classical geometries. Why are they at the beginning of a talk on symmetric spaces? Well, because they have lots of symmetries. And basically, what you see is that all points look alike in such a space, and you can easily see that if you take just 2 points, x and y, in your space, any of these geometries, and then you take the midpoint, which you can do because on each of these spaces you have a metric, you have a distance. So you take the midpoint, you connect these 2 points by a geodesic, take the midpoint, and then what you do is, at this midpoint, you take any geodesic that you have there and you reflect along this geodesic. You travel forward or backward, same amount of time. That's what the symmetry is. And in this way, you can move x to y. This means you have a symmetry preserving all the structure you have, moving x to y. So things look locally alike. So you have homogeneous spaces. And you can even give all symmetries. So in these examples that I did, you can look at the flat symmetries. So they will be translations, rotations, and reflections. And actually, so we've seen this example on Wednesday when we talked about two sharp transitive groups. That was an example. That was the key example that we had there. And for the spherical ones, you can do rotations and reflections. Let's not worry about this too much here. You all know that. And the hyperbolic one we have seen as well on Wednesday. That was the free sharply transitive groups, right? These were these fractional linear transformations. And if I write this in such a way that A, B, C, D, as it's written there, is real, then we're talking about the half-plane model, because then the upper half-plane will be preserved. But you can embed this into the Riemann sphere, and then you look at whichever subgroup you want to in SL2C. You get different types of realizations of this set of symmetries. Okay, so these classical geometries are the prime examples of two-dimensional symmetric spaces. Now, in general, you can go along this way, use the metric, use the symmetries, and if the metric is such that the construction I gave you with the midpoints actually works and maps, gives you a transitive action, then you have a symmetric space. But that's not what I want to use here. I want to give a description using Lie theory. So let's take a real Lie group. Just visualize SLN. So invertible matrices determinant 1. Then we talk about a subgroup, which is the group of fixed points with respect to some involution. Like in this example of SLN2, you could think of the involution, take a group element, take its inverse, take the transpose of the inverse. That's what I mean by this notation minus T or minus top in LaTeX speak. Then the group of fixed points, that's just SON. And now the symmetric space is just the quotient space. That's a G mod K in this situation. So that would be a symmetric space, and the symmetric spaces I want to look at all come about in this way. So, example, if you take that particular example that I showed you, what you get is, for instance, the n by n matrices of determinant 1, which are symmetric. The action is easy to write down. You take the identity matrix, which is a matrix of that type, and then you conjugate. And, well, from the left you take G, from the right you take G transpose. It's not just the ordinary conjugation. You do that, and then you get the symmetric one again, and the orbit will be just these matrices. And if you take n equal 2, you get yet another model of the hyperbolic geometry. That's a hyperbolic model. Okay, so what kind of symmetric spaces do you have? Well, there is a concept of irreducibility there. So if you take these irreducible, not decomposable into as products of smaller spaces, then you basically have 3 types of such symmetric spaces: flat ones, which are covered by Euclidean space. And if you want to write the obvious example Rn in the fashion I just explained with the group and the subgroup, then you take a semi-direct product of the rotation group with the translation group, mod out the rotations. That's what you get in this fashion. And I guess I don't have to, I mean, I was thinking about which parts does one have to explain in a talk or not. I decided I don't have to explain anything that has been explained in one of the plenary talks before. So semi-direct products came up. I remember that distinctly. So I don't have to explain that. Now, non-compact type. I take a non-compact simple Lie group like SLN-R. So if you're not familiar with Lie groups, or if you don't like Lie groups, but rather say algebraic groups or whatever, think of that example, SLN-R, that's fine. If you even don't like that, think of SL2R, that's fine too. You'll get something like 85% of what my talk is about. This example we just looked at, that's of non-compact type. In terms of curvature, it says negative curvature, or to be more precise, non-positive curvature. That's what these spaces are. First family, the flat ones are flat, which means 0 curvature. Compact type, so you take a compact simple group, like SON, but you could also take another one, easy to write down, SUN, the unitary matrices of determinant 1. And if you now look at complex conjugation on those, you get a fixed point group, and then you get a symmetric space of compact type. That's not what I want to talk about. I want to concentrate here on the non-compact type. And now, so far, I only talked about Riemannian symmetric spaces. I want to mention here, or it will be important to talk about locally symmetric. That just means that you take a discrete subgroup of the group G, of the big group, acting by isometries, and mod it out. So take a discrete subgroup, like if we take the example SLN-R, take SLN-Z, invertible integer matrices, and mod them out. So you have a double coset here, or the set of orbits on a space, on a symmetric space, like these geometries we had. So prime example would be the modular surface. You take hyperbolic geometry in the form of the upper half plane model, and you mod out the action of SL2Z, and then you get something. Yeah, I didn't produce a picture here, but if we do this, there is one picture everybody knows from complex analysis. So if we let SL2Z act on the upper half plane, then this part here, or a piece like this, is part of a circle here. This is 1 plus 1/2. This is minus 1/2. So this will be a fundamental domain. So this will be a surface with a cusp. So there will be singularities. In the Poincaré model, this would look like this, like a triangle which has this cusp up there. So if I say locally symmetric, Riemannian locally symmetric space, think of this. And these two sides are identified. These 2 points are identified actually. So this, the left half of this circle piece is identified with the right half. So you bend things together so it sort of looks like an onion, right? So imagine this onion, that's a locally symmetric space. Okay, so why would I want to look at this? There are 3 topics that I draw my motivation from to look at these objects and look at analysis on them. One is automorphic forms. As you can sort of guess from the example of the modular surface, so this has to do with modular forms, it has to do with mass forms. So that's something that's kind of obvious that you want to look at this. Then there is quantum chaos. That's the question how the passage from classical to quantum mechanics behaves when the classical system shows chaotic behavior. Typically, chaotic behavior is a nonlinear phenomenon, whereas quantum mechanics is described by linear objects. So it's not so obvious what you do there, and one can see that spectral behavior of operators is different depending on whether the classical counterpart was chaotic or not. So that's one thing. And then there's just geometric analysis on manifolds, non-compact manifolds, manifolds with corners, manifolds with cusps. And there has been a lot of activity over the last 30 or 40 years in this direction. And these locally symmetric spaces provide nice examples of such manifolds. And now here's so this is big field. Like I by no means can cover everything here. I mean, not in this talk, but also not in a lifetime. But the special features that are interesting for me and where I try to sort of invest my knowledge is this. In all these contexts, you see a connection or an interplay between symplectic dynamical systems, classical mechanics, and spectral theory of differential operators, or more general linear operators. That's quantum mechanics. And so typical interplay features would be trace formulae, which, for instance, relate something like the spectrum of a Laplacian with the distribution of lengths of closed geodesics. So that's a typical thing. Then semi-classical limit that in microlocal analysis, I mean, if you speak about quantization in a very, very general way, you'd say, okay, classical physics is commutative algebras, quantum physics is non-commutative algebras. I mean, don't jump at me for this statement. It's oversimplified, of course. But then you, what you look at, for instance, we saw in this last talk, there was this talk about quantum groups. There are certain parameters in these algebras, and these parameters, when they go to the limit, then you get a classical algebra, like a commutative one back. And this is similar in analysis. There's the semi-classical limit. So that's something. And then there's the the wording geometric quantization, that's something that comes up in mathematical physics, but in particular it comes up in representation theory. When you start out with geometry, symplectic geometry related to the group you want to represent, and construct from that a representation of that group. So starting with geometry, ending up with linear operators. So those are the typical, or some typical aspects of this interplay that I have encountered in my mathematical life so far. And the symmetries play the role that they give you additional power to treat the examples, because you have extra methods. You have nice examples, which you can, I mean, the basic idea is you have a set of core examples and you want to understand those, and then you want to perturb those examples and see what survives. Okay, so let me be a little more specific. That's another thing I was thinking about. I mean, what's the degree of detail you want to do in a talk like this? So far, half of you would say, well, what's he talking about? It's all non-mathematical. So let's be a little more mathematical here. If we talk about a symmetric space like this, we have one of these non-compact simple Lie groups. Then we have a typical decomposition, that's the Iwasawa decomposition. In the example I told you to keep in mind, the SLN example, that's a decomposition you all know. That's just Gramschmidt orthogonalization. Because what you do is you visualize an invertible matrix as a basis of a vector space, and now you make it orthogonal. What do? You start with one thing, and then you do linear combinations of what you had before, and in the process you have to do some normalizations. And that's precisely what's happening here. The n are upper triangular matrices. That is, you act only on matrices that you have been dealing with before. And the a's is diagonal matrices. That's the rescaling of the matrix. And the end result will be an orthogonal basis, and that will be an orthogonal matrix. That's an element of the K. Right? So this is Iwasawa decomposition is just Gramschmidt orthogonalization. Here's another piece of structure that one looks at. Namely, one wants to look at the centralizer in the group K of this A. So visualize diagonal matrices. You want to find all the orthogonal matrices that commute with all the diagonal ones. And if they don't commute, but they keep the diagonal structure, then this will be in the normalizer of the A. And the quotient of those two, that's the Weil group. That's an important feature of structure theory of Lie groups. And for SLN, it's very simple. The result will be just a symmetric group permuting the diagonal entries of the diagonal matrices. So you have that. Now, things become more complicated, a little more complicated. You take this subgroup K, which is a maximal compact subgroup. You mod out the M that I defined just before. And what you get is a compact homogeneous space. And you call it the Fürstenberg boundary. In some cases, namely in the case where A is one-dimensional, this will be a topological boundary. So for instance, for the upper half plane, what it will be is just the real line plus infinity. Or in the Poincaré disk situation, it will be just the topological boundary. In general, it is a more complicated kind of boundary, which you could describe in functional analytic terms. I don't want to go into this. But now there's an interesting feature. Look at this quotient G mod M. Now, M is the group of, that centralizes A. So we can let the A act from the right side on this quotient space, which is not, which you couldn't do if this weren't commutative. So you could only let it act on the left. But here you can let it act on the right. And that's an action of this abelian group A. That's what's called the Weil chamber flow. Okay, so you may say, well, what do I care? If you take the upper half plane, this action will be the geodesic flow. So that's a very simple way to characterize the geodesic flow on such a symmetric space, and then you can calculate with this geodesic flow in a very efficient and elegant way. Now here's another piece of information one wants to have. One wants to have the Laplace-Beltrami operator. Implicitly, it has been used over and over again during this week, but you can do this for general Riemannian manifolds. So let's not worry about it. And it will be of crucial importance. Let me give you an example. Upper half plane. It looks like the Euclidean, Laplace operator, but it has this extra stretching factor, which comes from the fact that towards the boundary, the metric is stretched. And here is another very important piece of information about such a non-compact simple Lie group. That's the space of invariant differential operators. So the group acts on the space, so the group acts on the functions. And since the group acts on the functions, it acts on operators on functions, in particular differential operators. Since the group action is differentiable, it acts on differentiable operators. And for the upper half plane, this algebra is a simple algebra. It's just generated by this Laplacian. In general, it's a commutative algebra. That's a special situation for symmetric spaces. But it has more generators. So that's a little complicated, and one thing why we all hate these projector talks is that definitions go away so quickly. Like here, some people write something, whether it's notes or not. Let's assume it's notes, taking notes. So now they are frustrated because it's a way. So let me repeat what I just said just in rank 1. So in rank 1, the Weil group is very simple. It's just plus and minus 1. You have a one-dimensional space on which this acts, so you just reflect. This K mod M that I had, this boundary in rank 1, can be identified with the unit sphere of the tangent bundle of the symmetric space. And that makes sense if you talk about geodesics, because if you want to compactify such a manifold, so you want to take geodesic limits, so you start with something on the unit sphere, and then you take a geodesic parameterized by this vector, and you move out to infinity. So the unit sphere should be compactifying the space. The G mod M on which we had this action actually is the sphere bundle inside the tangent bundle. So that's easy to see. And then it makes sense that the geodesic flow should be an action on this one, because geodesic flow preserves length.
Could you take the microphone?
Up? Yeah, okay, sorry. Right here, I sound very loud. Yeah. Okay. Oh, because of this one. So, thank you. Okay. So, well, as I said, this is now for in general what is true for the upper half plane is true in general geodesic flow. And then we can compactify, put on the metric. And if we take these geodesics and we don't care about the parametrization of the geodesic moving around, then we just can take the endpoints, and it can also be parametrized in group theoretic terms. So it will be just this homogeneous space G mod MA. Okay, so now I spent 3/5 of my talk on introduction and motivation. Don't worry, I don't want to, I will not take over time, I promise that. Okay, let me talk a little about non-commutative harmonic analysis. I want to talk about Fourier transform, and I want to talk about Poisson transform. Those are the two things I will need. I leave out Radon transform for time reasons. Now, there are a number of names associated with the non-commutative version here. This is Gelfand, Harishchandra, Helgason, Kashiwara, Oshima, Schlichtkol, Vandenbahn, many others, but those are the ones who proved the decisive theorems that I will sort of summarize now. Let me recall flat Fourier transform, even though I should really leave this out because it's been mentioned over and over during this conference. But I want to make very clear the analogy between abelian and non-abelian harmonic analysis. So the principle of Fourier transform, at least on Rn, is write functions as superpositions of plane waves. So we saw this yesterday in the talk about Roth's theorem. There it was characters, really. So that was a different situation with harmonic analysis on finite groups. But here we do it this way. And here's the superposition. So the red thing is a plane wave. So these are the waves we saw on Wednesday. I mean, these ocean seas, as they were called, are these plane waves. And we write the function as a superposition of those. And I added a rewriting of this formula in terms of polar decomposition because that brings out the analogy to the symmetric space situation. So then one knows that you can actually do this by using these Fourier coefficients that are in the second line here. And the first one is Fourier inversion theorem. Okay, so what's important here? Well, group theoretically would say these are characters. But I rather want to stress here these are eigenfunctions of the differential equation of the differential operators, constant coefficient differential operators, right? But constant coefficient differential operators are differential operators that are invariant under translation. So this is the analog of the algebra of invariant differential equation operators that I was talking about before. And the fact that you all know is that Fourier transform intertwines constant coefficient differential operators and multiplication by polynomials, and that's a key point why it's so useful to use Fourier transform in dealing with linear differential, partial differential equations. Now let's do the same thing for these hyperbolic situations, for these non-Euclidean situations. Same situation. The principle is again, write functions as superpositions of plane waves. So there is a function family of plane waves, but now in a way I already write the parameters as I wrote them before in terms of a kind of polar decomposition. And I don't want to say what these functions are. They are exponential functions plus some structural functions from the Iwasawa decomposition, to be sure. But you see the structure of the formulas is just the same. And all the other things, the principles that I showed you, are also all the same. So these plane waves are eigenfunctions. And what one has to explain is the measure, the d bar lambda in the first line. It's a special measure, like in the polar decomposition we had not just dr, but rdr or r to the n minus 1 dr, depending on the dimension. That's the same case here. So we have a special function coming into this, and the special function is coming from Harishchandra's C function. So I put it here just to show you that this is not trivial. I mean, it's very similar, but it's not trivial. And then there's the same principle about commuting the Fourier transform, intertwining differential operators and multiplication by polynomials. I mean, polynomials at least in one of these variables. Okay. Just to show you that this is not all trivial. I mean, these things for Riemannian symmetric spaces are old. This was finished in the 70s. Then people took a long time to do it for non-Riemannian, was finished in 95. Lots of very good people worked on that. There is now an effort to do this for superspaces, and so supermanifolds that have similar structure as Riemannian symmetric spaces, and you want a Fourier transformation, Fourier inversion formula. And so this was started with a paper on the Poincaré disk by the physicist Martin Zirnbauer, and then nothing happened for a long time. And he was trying to get Lie group people into this, but whenever Lie group people entered the field, they soon started to do classification of superspaces, and nobody wanted to do the analysis part. Okay, so it took a long time, and then we took this up together with Zirnbauer, and we proved some things in the direction. So we are not there yet. This is just to show you that these generalizations of Fourier inversion need not be trivial. You need a lot of material to do in between, and there are just names. So let me not explain them, just names. They follow the strategy for the symmetric spaces, but they are more complicated. They are more involved. And that's why you have to do it one by one. So it's hard work. And by now, it's Alexander Aldrich in Cologne who has taken the lead in this. And sooner or later, he'll do the Fourier inversion, I'm sure. OK, Poisson transform. Take a function on the boundary. Take a distribution on the boundary. Take a hyperfunction on the boundary. Poisson transform is just integrate this function distribution hyperfunction against these plane waves. What you get is a function on the entire symmetric space. And this function has lots of nice properties. It will be an eigenfunction of the invariant differential operators. And a difficult problem is to show that these Poisson transforms are actually invertible. Almost always. There are certain exceptional values for lambda where they are not. And the inverse is taking some kind of boundary. But mind you, taking boundary values for things that have very rough boundary values, it's not a trivial thing. So this is one of the triumphs of Japanese algebraic analysis. So this is so the input of Kashiwara Oshima and other people using Saito's hyperfunctions, where they actually proved this invertibility. Now, there is a simple version or a simple case where you can show that these are invertible. There's Weyl group invariant polynomials, and this piece are A. So the A is just another version of the big A. It's just a vector space. So you have polynomials on that. Then you have this important thing, the Harishchandra isomorphism between differential operators, abelian, and this algebra of polynomials. So that's an important feature that you have here. And then you have these eigenspaces that I just said. And so what you can see then is if you take such an eigenfunction, then you can take boundary values and get back invert the Poisson transform. Okay, so this looks technical, and I don't want to spend time on this here. This is what I wanted to say about non-commutative harmonic analysis. Fourier transform, superposition of plane waves. Poisson transform, writing functions as integrals over boundary values. Microlocal analysis. So what is it? Well, Euclidean microlocal analysis, you take symbols and associate operators. Now, with what we've seen from Fourier inversion, it's no problem. We take the Fourier inversion formula, plug in some multiplication. If it's a polynomial, then it's a differential operator. It's not a polynomial. It's something else. It's a pseudo-differential operator. So this is how Euclidean microlocal analysis works. Non-Euclidean, well, do the same. We have a symbol which lives on the space and the dual variables in the Fourier inversion. Just like before in the Euclidean one, you have the symbol depending on a variable in the space and the variable in the dual. And do the same thing, do the Fourier inversion. Now, there are subtle points in this. This, as a calculus, only works in rank 1 reasonably well. In higher rank, there is a problem that has to do with the singularities in this type of product decomposition, these product polar decomposition of these spaces. Don't want to go into this, but there's another way to do this. Now, if you want to, if there is an analyst in the audience who wants to take something home, here is something to take home. This is not new, goes back to Widom and was worked out nicely by Sharafutinov, is a pseudo-differential calculus that works on Riemannian symmetrics, Riemannian manifolds, and is very nicely adapted to symmetries. So I recall here, so look at the upper two lines, you see the formula for the operator. You see that there are differences coming up. Now, in a manifold, you cannot do differences. So what do you do instead? Well, you do with what we started out with, namely, you, instead of taking the difference like in flat space, you follow along a geodesic. So one replaces the difference up here, this one, by taking a tangent vector and moving over here. So where do you end up? Well, you take the Riemannian exponential function, start at x, follow up the v, and then you end up at the endpoint of this geodesic. Otherwise, it's the same formula, you just integrate over the tangent spaces. Then there is a little problem, technical problem, that these exponential functions may not be injective. So there's a radius of injectivity, and therefore you have to use a cutoff function, which is the red thing. That's a technical thing, but you can use invariant cutoff functions here. That's very nice. Okay, so let me go and end up with a bunch of theorems, right? So now I will not be able to explain everything in detail. So if you say, I've had enough, now you can sort of shut down. But I will explain what this has to do with quantum ergodicity, which is an interesting field. So you look at eigenfunctions of the Laplacian. You look at high frequencies, eigenfunctions for high frequencies, and then you define what's called the Wigner distribution. You take some symbol. You take the operator that is associated with the symbol using the microlocal calculus that I just explained. And then you have to use the microlocal analysis that this is a bounded operator, so you need L2 boundedness. We've seen this yesterday, was an important thing. In Hermann's theorem, you have this in microlocal analysis just as well. And then you can prove a little lemma, And that says, well, this family of distributions will be bounded in the space of distributions. And if this bounded thing has a limit, then this will be called a lifted quantum limit or a microlocal lift. There comes under different names. And if it exists, it's a probability measure. Now, here's the question of quantum ergodicity. That's been solved. There is, you can always pick a subsequence converging. That's quantum ergodicity. If you can show that there's only one limit possible, that's quantum unique ergodicity. That's an open conjecture by Sarnak. That's the reason why people are interested in this a whole lot, and they want to study properties of these limits in order to get information for which kind of limits you can have. So that's a question, and so there's a lot of work on this. And using the microlocal analysis approach, what you can do is, if you have such a limit under certain technical conditions, you know this probability measure will be supported on an orbit, one thing. This limit will be invariant under the Hamiltonian flows coming from the symbols of invariant operators. And with a certain regularity, under a certain regularity condition, it is also invariant under the Weil chamber flow. Silberman and Venkatesh Silberman wrote an extra paper to do the singular case as well, because they needed to do a different lift kind of thing, and then you can do singular limits as well. So our proof does it in one thing. The result looks a little different, but it's the same proof. So you can do it. Generally, it's propagation of singularity techniques that you use here. So you have that. This I will skip. It's a technical thing. It's a technical thing. But what it does is the following. So you have these Wigner distributions. They go to these quantum limits. The Wigner distributions don't have any good invariance properties. They look awful. But in the limit, you have these nice invariance properties I mentioned. So the question that was put forward by Anantaraman and Zeldich was, can you replace these Wigner distributions by something that already, before you go to the limit, has good invariance properties? And that's what these Peterson-Sullivan distributions are. And they proved the theorem about hyperbolic surfaces, and we could do this in general. And here's the function that has the singularities. Never mind. What's interesting about this is these distributions, you could say, well, Wigner, Peterson, invariant, well. But these Peterson-Sullivan distributions do have a classical interpretation. Classical mechanics, they can be interpreted in terms of dynamical zeta functions. And that worked nicely for surfaces. We can do it for hyperbolic spaces. We cannot do it for spaces of rank 1 in general, let alone higher rank. That's something we don't know how to approach. Even the dynamical zeta function should be several variable functions. Okay, but it's what this is a connection again between classical and quantum. And well, I had these resonances. That's lots of work in progress anyway. So let's skip that. Oh, lots of theorems there. But let's not worry about this. Old theorems, new theorems, scattering, new developments, open problems. Let me jump to the conclusion. I mean, that's not something you tell mathematicians to do, right? Let's not jump to conclusions. Okay, well, let me jump to conclusions here. There is plenty of, so I just gave you this movie. There are plenty of results connecting symplectic geometry and spectral theory of locally symmetric spaces. Resonances are, for instance, resonances for Laplace operator and other things. But these results are of a very diverse generality. There are certain results that only work for hyperbolic surfaces. So in part, they are older results that have been replaced so far, but in part, they still stand as the top-notch results. Some results are true for hyperbolic spaces, like the equivalence between various kinds of resonances that are in the literature, Laplacian resonances, scattering matrices, real resonances. That works for hyperbolic spaces, but not for rank 1. Certain things, like the super things, are true for rank 1 spaces. Certain things are true for higher rank. So there are lots of open problems here, but if you analyze closely, when you do this transformation between classical and quantum, whatever you do, whichever result you look at, somewhere Poisson transformation is doing the trick. Sometimes it's really hidden in the term under the disguise of period integrals, for instance, in the automorphic form situations. But it's always the Poisson transform. And well, that's something I would like to understand better, and that's the plan for the near future. Now, being the last speaker of this conference, I want to take the opportunity to say thank you to you all for listening to this last talk, for even coming to this last talk. I want to particularly thank all the young people that I've seen during this week, working very hard, never get mentioned anywhere. Thank you very much.